Okay. So far we have seen that your superposition theorem. So next we will go for source transformation. Actually, this source transformation will simplify the circuit analysis, and sometimes it is easy to solve the circuit of computing branch current or voltages whatsoever. So things are simple, but we have to try to understand certain things, right? So this is actually basically this is a concept of your what you call equivalence, right? And equivalent circuit is one whose VI characteristic are identical with the original circuit. For example, whatever I have written. For example, you consider this source transformation, right? If you look into this circuit, that this is your this is a voltage source V and this is the resistance R, right, and this is the voltage source B. So this is actually bilateral. I mean, either from this circuit you can convert it to your current source or resistance are in parallel or in other way, and terminal 1 and 2 is marked, and this circuit can be equivalent to this one at terminal 1 and 2, but VI characteristic at terminal 1 and 2 has to be same for both the cases, right. Now before your how we are getting from here to here, and what is the that VIR relationship, what is equal to I, just we will see everything is given at the bottom, but let us see how we can do it. For example, suppose first let me clear it, and then suppose I connect a resistance RL here. Suppose this resistance is RL. We call generally RL means stands for a load resistance. Suppose current through this is IL, right. That means same current is flowing to R and RL because both are in series. So if you write the expression of IL, then your IL is equal to V divided by R plus RL, right. This is the current that is flowing through the resistance RL. Suppose we have connected resistance RL. Now for this circuit also, because at terminal 1 and 2 this VI characteristic of both the circuit has to be same. It is, I mean, both circuits are equivalent to each other. Suppose if we connect a same load resistance RL, this is also RL, right, and current flowing through this is say IL, here also IL is flowing, here also IL is flowing, and this current source, that is independent current source, for the time being we have considered independent voltage source and independent current source. If the this current flowing to RL, you can find out that IL is equal to the current division method, that is R divided by your R plus RL into this I. This is the current source I. This IL and your what you call this IL and this IL both have to be same for equivalent. Here it is V upon R plus RL, here it is IL is equal to the current division R upon R plus RL into I, right. If both are equal, that we can write, somewhere I am writing, we can write that V upon R plus RL is equal to your R upon R plus RL into I, right. So R plus RL will be cancelled both sides. So ultimately it will become V is equal to your R into I, right. That means this I is equal to actually V upon R, right. This is that means voltage drop IL into RL, and here also IL into RL, this has to be same. V is equal to your, I mean, that is the idea, right. So that means this is a source transformation. That means from the if you have a voltage source and a resistance R like this, you can convert it to the current source, right. And from the same thing, if it is your I and it is R, they represent this one, that from it is a bilateral, from this current source and this parallel resistance you can make it V is equal to IR. This is the voltage source, and with V this R is in series, right. All these things are given downwards, but this is for your understanding. Now question is that this is your what you call that and direction of the here your polarity is plus minus. So current I is showing your plus minus, that is current is flowing out from here. Here also current is flowing out from here, right. So that's why this, when you just let me clear it, that means whenever you are going for this transformation, that if I go for V and on R is in series, then I is equal to here it will be V upon R, right. This is V, this is R, and from this kind of your current source and this resistance is there in parallel. If you transform this current source to the voltage source, then this V should be is equal to IR and this R should be in series, vice versa, right. So, similarly, one more thing. So, this is how we do it, but look at the polarity plus minus. So, current direction here in the independent current source, it is upward, right. Now, suppose instead of that, suppose if this is my, if this terminal, for example, if it is minus, if it is plus, right, then here also current direction should be downward. So, according to looking at the polarity, that arrow tip should be at the plus. So, current direction should be downward, rest will remain same as it is, rest will remain same as it is, right. So, only polarity you have to check here, if it is plus minus. So, plus tip means this arrow one, earlier I told you. So, it will upward, and if it is just, if you reverse it, then it will also reverse, right. So, current direction should be, in that rest will remain same. So, this is actually source transformation for independent sources. Now, it is true also for dependent sources. So, let me clear this, right. So, all this whatever I said, all these things are written here for your understanding, right, and all this whatever I wrote on the blue ink, right, everything is there, but there here there circuit, everything I showed how to do it. Here I have not drawn it, but I showed you the beginning, right, and these are all same, and just you will go through step by step, everything is written here, but I explained that how that electrical equivalent, that I is equal to V upon R or V is equal to IR. Now, that means if the polarity also I told you, this polarity also I told you, that if the polarity of V is reverse, the orientation I must be reversed to maintain equivalence, that I just told you, the underline also, right. So, let me clear it. Now, source transformation also applied to dependent sources. For example, if it is a later we will see that when we will consider that your numericals, for your containing your considering your different type of dependent sources, voltage or current. So, if your this thing this is the voltage source, a dependent voltage source, right. So, it is also bilateral. So, it will be also your dependent current source. Later we will see this, right. So, same way we can transform that in your dependent voltage or current sources. Now, consider one example. Using source transformation, you determine V0 in the circuit. For I mean this is your V0. So, you have to find out the V0 in the circuit and so on, and one independent current source is there, this is 4 ampere, and one independent voltage source is there, that is 12 volt, right. So, this direction, look at the direction here, it is upward, right, and when you convert this one, so I mean this portion, when you convert this one, your this current source and one resistor is there in parallel. If you try to convert it into the your what you call, judiciously you have to make it into that your voltage source and resistance in series, the resistance this 3 ohm is in series, then 4, that V is equal to, it is 4 into 3, that is your 12 volt, that is 12 volt, right, and this will be the equivalent voltage. I mean we are transforming this portion only from your current source to the voltage, but look at this, it is downward. So, if I draw it here for this portion, this will be minus, this will be plus, right, this will be my 12 volt, and this resistance is in this ohm, it will be 3 ohm, right, this will be 3 ohm, and this 3 ohm and this 3 ohm, then both will be in series. Later we will see the circuit, right. So, similarly, here also if you have this 3 ohm and this is 12 volt. Now, if we want to convert it to the your, suppose for example, this portion, if we want to convert it into the your current source and the resistance, this 3 ohm will be parallel, then I is equal to 12 by 3, that is equal to 4 ampere, right. And then if we try to represent it by current source, then what will happen, this 3 ohm resistance will be in parallel, and this will be your current source, arrow is upwards, right, and because here plus polarity is here, and this will be your 4 ampere, right. So, if we do so, then circuit your what you call configuration will change. So, let me, so before everything is there at the bottom, but before that I am just trying to explain that how we actually obtain it. So, let me clear it, right. So, if you go there, here look this first what we have done, that this one we have this portion we have converted to 12 volt. I told you this is 12 volt, and I told you the polarity also, because current source, that is your, it is downwards, right, and this 3 ohm, and this 3 ohm is in series, and similarly this one converted, polarity was upward. So, it is your arrow is upward. So, this is 4 ohm. So, this way this side portion we have converted like this, and this side portion we have converted like this, right. So, after this our objective is that we have to find out V 0, right. Next what will happen, these 3 and 3 both are in series. So, 3 plus 3 it will be 6 ohm, right. So, now this portion of the circuit, is volt 12 volt, and this 6 ohm as in series, you convert it to a current source, and in parallel you put 6 ohm resistance. If you do so, then current I will be is equal to 12 by 6 is equal to 2 ampere, that is 2 ampere, right. That means this portion it will be somewhere, I am just clearing it, I am just hold on, I am just clearing it. Then this portion it can be made it like this, look, plus is here at the bottom, right. Therefore, this is your 2 ampere, and here this 3 plus 3 6 ohm. So, this 6 ohm will be in parallel, right, and after that you connect that circuit as the whatever way it is given, same thing, and this 4 ampere let it be here. So, both the things we converted to a current source, right. So, let me clear it. So, if you go to the next one, then this is your, here just let me go a little bit up. So, this is your the 2 ampere downwards, and this is 4 ampere your upwards, right. So, now all three, this one, all three are in parallel, right. So, because this is your common node, no electrical elements are connected here, common node. So, 6 ohm and 3 ohm they are in parallel, but we have to find out V 0. So, we cannot eliminate 8 ohm, but 6 and 3, 6, 8, 3 all are in parallel, but take the equivalent of 6 and 3, these two are in parallel. So, this thing is parallel is 6 into 3 plus divided by 6 plus 3. So, is equal to 2 ohm, right. So, this here it is 2 ohm, this is the parallel of this thing. This 8 ohm is written, and this 2 ampere is written, and this 4 ampere is written, say, right. So, that means further simplification, then you clear it, right. So, once if you show, if you look into this, that this 4 ampere is upward and 12 ampere 2 ampere is downwards, right, and this is your what you call common node, all are in parallel, this one all are in parallel. So, resultant of 4 ampere it is upward and it is downwards. So, resultant will be 2 ampere upward, that is your 4 minus 2 ampere, that is equal to 2 ampere, it is upward, right, because this is 4 up, this is down, and equivalent is 4 minus 2 ampere, because all are in parallel. From your intuition you can easily make it. So, this is 2 ampere because of the resultant of this, and this is 8 ohm and this is 2 ohm. After this you go for current division, right. So, if you go for current division, this 2 ampere current, this is my 2 ampere current, right. Then what is this I? Now, we have to, the current division we will find out I is equal to, right, it is flowing to, what is the current flowing to 8 ohm resistance, this will be 2, right, this 2 divided by 2 plus 8 into 2, that is actually 0.4 ampere, right. So, that means your V 0 is equal to 8 into I, because this is 8, this is I, 8 into I. So, is equal to 8 into your 0.4 is equal to 3.2 volt, that should be the answer, right. So, this is how we do it. So, let me clear it. So, all these things have been explained and solved. You just go through what I told, right. So, everything is written for you, just to go through it, that how we have solved. So, slowly and slowly come down. So, this is your, I told you that this is your answer, that 3.2 volt. I solve everything for you, but everything is written here. So, you can easily make out that how things are. When you will go through this video, at that time you can make it, but everything I have explained, right. So, take another one. So, now using source transformation, determine Ix in the circuit you are shown in figure this 14, that is, it is topic 4. So, this thing, one dependent your what you call voltage source is there, So, it is dependent voltage source is there, and this is your 4 ampere your independent current source, and you have to find out what is Ix, that is the thing, you have to find it out. Now, question is that this dependent voltage source and 5 ohm, they are in your what you call these 5 ohm and these two are in series. So, you try to convert it to the your what you call dependent current source, same transformation, same philosophy here, right. So, if you do so, this is for example, this dependent your voltage source. So, if it is your 2 Ix, right, V is equal to say to polarity, look here is bottom, right, plus, right, and if V is equal to 2 Ix, then I suppose if I want to convert it to a dependent your current source, then I will be is equal to your V divided by this 5, because this 5 ohm is there, and V is equal to your 2 into Ix divided by 5 is equal to 0.4 Ix, right. So, dependent voltage source will be converted to dependent current source, right. So, it is 0.4 your 0.4 Ix. Now, if you try to represent that one, let me clear it, right, let me clear it. That means, because plus is here, so arrow tip will be downward, right. So, it will be your 0.4 your Ix, and with this 5 ohm resistance will be in parallel, 5 ohm resistance will rest to connect with this, right, rest to connect with this. So, this is actually how we can convert it, same philosophy, dependent or independent, same philosophy. So, let me clear it. So, if you go to the equivalent one, then circuit is becoming like this, circuit is becoming like this. I told you that this arrow will be downward, look at the polarity, and 0.4 Ix and Ix 5 ohm, this is 10 ohm, this is 5 ohm, and you have to find out the current through this, right. Basically 10 ohm and 5 ohm both are in parallel, right, but we will go for current division, and this is 4 ampere. Now, if you now move go for current division, right, if you look into your this thing, what we have made? We have made Ix is equal to 5 by 5 plus 10, 4 minus 0.4 Ix. How it is coming? This is this one actually, this is upward, this is your downward. So, if you make a resultant of it, it will be actually your 4, somewhere I am writing here, it is 4 minus 0.4 Ix, right. I mean, direction will be upward, not putting here, this direction of this one will be upward, and this current is divided into 10 ohm and 5 ohm. Therefore, current division method, your Ix will be is equal to your 5 divided by 10 plus 5, right, into your 4 minus 0.4 Ix, right. So, basically it is 1/3, because 5 by 15, then 4 minus 0.4 Ix. After that you solve for Ix. So, you have to from your intuition you have to make it, that how to solve this circuit. So, let me clear it. So, if we go to this one, so it is given that after solving this one, you are getting your what you call Ix is equal to 1.176 ampere. Things are easy, just you have to from your intuition you can solve it, that how to do it, right. Next one, let me clear it. Next one, using source transformation technique, determine the current through load resistance RL is equal to 4 ohm in this figure 16, right. So, you have to find out your you have to find out your current through this 4 ohm resistance, although 4 and this 4 and this 4 both are in series. So, effective will be 8 ohm, but you cannot remove this 4 ohm, because you have to find out the current through this load resistance 4 ohm, right. So, this one, this side, if you look into that, this is 12 volt source and polarity is plus minus, this is plus, this is minus, 6 ohm. So, if you want to convert it to a current source, right, only this portion, if you convert it to a current source and a resistance parallel 6 ohm parallel to it, therefore, I is equal to your 12 by 6, this 12 by 6 is equal to 2 ampere, and your arrow direction of the independent current source will be upward, right, and at that time this 6 ohm will be in parallel to this 12 ohm and other with this 12 ohm, right. So, if you convert this one to this portion to a current source and a 6 ohm in parallel, then look how the circuit will look like, right. If you do so, look, this 2 ampere and this is your what you call, this is your 6 ohm, right. See, this after this transformation, and this 12 ohm is there, and this 4 ohm and this 4 ohm, this one is there as it is, right. Now, once you have done this, then this 6 ohm and 12 ohm both are in parallel. So, you find out their equivalent, that is 6 into 12 divided by 6 plus 12, that is actually is equal to 4 ohm, right. 12 into 6 your 72 divided by 18, so 4 ohm. So, that means this 4 ohm is here, equivalent to this 4 ohm is here, and this is 2 ampere and this is 4 ampere, right, both are upwards, and RL and 4 ohm, these things are as it is, right. So, let me clear it, right. So, now what you can do is this current source and these two, you convert it to a voltage source, and series they put 4 ohm is in series, right. Therefore, V is equal to your IR. So, this is 2 ampere and this is 4 ampere. So, 2 into 4, that is your 8 volt, right, this is your 8 volt. So, here it is 8 volt and direction is upward. So, this is your plus minus, and that means this 8 volt and this 4 ohm, these two are in series. Along with that, this 4 ohm resistance was there. So, 4 and 4 both are in series, and this is 4 ampere, this part of the circuit keep it as it is, right. So, after transformation, so that means these two 4 plus 4, this is 8 ohm, right, they are in series. So, let me clear it. So, next is what we have done, that this 4 and 4 8. So, 4 plus 4, it is 8 ohm and 8 volt source is there. So, transform into a current source. So, I will be is equal to 8 by 8 is equal to 1 ampere. So, this is 1 ampere, arrow is here, a plus is here. So, arrow is upward. So, this 8 ohm is in your what you call is in parallel with this current source, and this 4 ampere and this 4 as usual it is there, right. That means, if you look into that, this 4 ampere is upward and this 1 ampere is also upward, and this your what you call this all these things, this one and this 4 plus 4, it is basically 8 ohm, but all these things are in parallel. If you look 1 ampere, 8 ohm, 4 ampere, this 4 plus 4, 8 ohm, all are in parallel. So, if you take the resultant of this 4 this independent current source 4 ampere upward, this 1 ampere. So, resultant will be your 5 ampere, right, resultant will be 5 ampere upward. So, let me clear this. So, that means 5 ampere is here, 5 ampere is here, here it is 5 ampere, because 4 and plus 1 both are upward. So, 5 ampere is here, and this 8 ohm is here, and this 4 ohm is there. So, from the current division method, basically this is also 8 ohm, this is also 4 plus 4, both are in series 8 ohm. So, actually current flowing to this is 2.5 ampere, this is 5 by 2. So, current division method, if I make it IL is equal to, it is 8 divided by 8 plus 4 plus 4, because these two are in series. So, 4 plus 4 into this current 5 ampere, it is 5, right. So, so it will become 2.5 ampere, right. So that is the answer, the current flowing through this. So let me clear it. So all these things are explained here. I told you everything, all write up is there. So you will, when you will go through this video lecture, if you have any difficulty, you can go through my write up, but everything I explain how to solve it, right. So all these things are explained, right. Finally 2.5 ampere. So after this, after source transformation we have learned, next another important thing is you learn, that is your Thevenin's theorem, right. So in this section we will learn how to replace two terminal circuit containing resistances and sources by simple equivalent circuit, that we have learned. As a typical example for that your simple suppose you have a large circuit, but your interest is to find out the current to a particular branch, and if that branch your what you call, and if the branch resistance is variable say, but rest of the circuit is unchanged, then the rest of the circuit we can find out to an equivalent your what you call voltage called Thevenin's voltage and equivalent resistance called Thevenin resistance. So how we will do this, right. Suppose for example say as a typical your what you call, as a typical example, the household outlet terminal connected to different electrical appliances constituting a variable load. Each time the variable is changed, right, the entire circuit has to be analyzed again. I mean, if you take a large circuit and one particular branch say R is changing, so again whatever we have studied till now, again and again you have to solve the whole circuit, right. So this is very much your cumbersome and it is time consuming process. So to avoid this problem, Thevenin's theorem gives a good technique by which fixed part of the circuit can be replaced by an equivalent circuit, right. So this is your what you call that Thevenin's theorem. So what it states. Now next is that your by a two terminal circuit, we mean that the original circuit has only 2 points that can be connected to other circuits, right. However, a restriction is that the controlling variables for any control sources must appear inside the original circuit. So here Thevenin's initially when first time, those who are studying first time, for them just you have to be very careful that how we will do it and how we can get it, right. So for example, suppose this figure, this thing, it shows a linear circuit. The circuit to the your what you call left of this terminal, this side left of the terminals, this 1 2, this is terminal 1 and 2 in figure your what you call is known as this is a figure, this linear circuit is given, two terminal circuit, and is Thevenin equivalent at the bottom it is there. So it was developed by M. Leon Thevenin. His lifespan was 1857 to 1926, and in 1883 he was a French telegraph engineer. So 1883 he gave this concept when he was 26 years of age, right. So that is your this is an equivalent. Suppose terminal 1 and 2 some load is there, and linear two terminal circuit, this is a big circuit to the left of this one, but some terminal 1 and 2 is there and some load is connected, and this may be variable load. I mean, suppose this load is changing, if every time this load resistance is changing, then whole circuit you have to solve, right. So but Thevenin's theorem suggests that if you just rest of the circuit, if you can bring it to an equivalent two terminal circuit, then and after that you connect this one, you can easily find out what is the current flowing through this load resistance R, right. So let me clear it. So its Thevenin equivalent says that this circuit, that this voltage, that V Thevenin and R Thevenin, right. So this is my V Thevenin, that equivalent one, this is my V Thevenin and R Thevenin. With that you connect this load in series with that load resistance whatever it is, right, and this is called V Thevenin. Sometimes it is called open circuit voltage also, VOC, later we will see. Sometimes V Thevenin we call VOC, right. So that is your what you call the Thevenin your voltage, that we have to learn how to obtain, and R Thevenin. when AC circuit will come, at that time instead of R Thevenin it will be Z Thevenin, that there we will see the impedance part, right, and current I is same, this current I is same. So, this is that Thevenin equivalent circuit, but how to do it? Okay, thank you very much, we will be back again.